Hello judges, we are Team 18219 Primitive Data, and this is our Control Award video submission. The most innovative part of our robot, mechanically and control-wise, is our swerve drivetrain. On a swerve drivetrain, each of the wheels steers and controls its velocity independently. We derive the inverse kinematics of a swerve drive, which means that we can provide a desired translational and rotational vector, which are used to determine the vector of each of the wheels individually. Now that we know where all the wheels should be using this algorithm, we implemented a custom PID controller with anti-integral windup to move the wheel to the desired heading. A PID controller reduces error in a system by calculating the current error, integral of the error, and derivative of the error, and multiplying these values by constants to output a power for the wheel to steer at. This combines for smooth and very responsive driving during auto and teleop. We also implemented a PID on the entire rotation of the robot, meaning that during the autonomous period, the robot will automatically adjust to correct its heading when it gets off. The final element of programming the swerve was using magnetic analog absolute encoders, which hold their position even when the robot is turned off. These encoders measure the heading of the wheel steering and can be bulk read to reduce loop times. These encoders do have a bit of noise though, so we implemented a low-pass filter. Low-pass filters use the previous measurements and the current measurement to make an estimate of the true measurement. This filters out noise but introduces a bit of phase lag. To make driving as easy as possible, there's one button for intaking and the 3 levels for scoring. These buttons initiate a sequence of automatically timed movements for the arm, the claw, and the lift. This makes scoring and resetting for intaking as easy as just pressing 3 buttons. Our algorithm for determining the randomization location during the autonomous period uses an HSV threshold. All pixels not in the threshold are turned to black, whereas those inside are kept as white. The average white value of each of the 3 sampling regions is calculated to determine where the team scoring element is. HSV is used because it separates hue from saturation and color intensity, making our algorithm robust under different shadow conditions.